Hi everyone, my name is Volkan. I am the head of Samsung's AI Center in New York. I'd like to start by thanking the organizers of Event-Based Vision workshop for putting together such a wonderful event and including our center as part of it. Before we get into the details of our work in Event-Based Vision sensors, let me take a few minutes to introduce our center. Samsung recently established a network of AI centers throughout the world to perform fundamental research that will inform future Samsung technologies. Robotics and perception technologies are expected to become key components of future consumer products. Samsung established the AI Center in New York in 2018 with a focus on robotics and real-time perception for robotics. We are physically located in Manhattan's Chelsea neighborhood. Our center is home to a great group of interdisciplinary researchers as well as cutting-edge state-of-the-art equipment. For a broader overview of Samsung's vision in the area of robotics, I would like to encourage you to watch our President Sebastian Song's presentation as part of the last CES. Within this context, we've been working on clutter management as a representative application for robotic manipulation. Here you see one of our earlier projects on a shoe organizing robot, which is able to identify shoes in clutter, compute grasps, and pick them up to organize the shoes. Here we see a newer iteration of the same system, which is capable of handling a broader set of objects, and the system integrates early perception, grasp planning, and motion planning. We have multiple projects on multimodal perception and control. Here I would like to give you two examples. The first video shows our collision detection and avoidance systems, where the robot uses acoustic surface waves to detect approaching objects and avoid collisions. In the second video, we show our tactile-based control system, where the robot uses tactile feedback to control the velocity of the sliding object. Of course, event-based cameras and dynamic vision systems have been a major focus of our attention. Before I turn over the presentation to my colleague Anthony Bisulco to give an overview of our work in this area, I would like to thank you for your attention and mention that we're always looking for great team members to join our center, and if you're interested, please feel free to contact us using the contact information Anthony will give at the end of his presentation. Anthony, your turn.
Thanks for the handoff, Volkan. Again, hi, my name is Anthony Bisulco. I'm one of the research engineers, a part of the Samsung Artificial Intelligence Center New York, working on some of our event-based perception research. Today in our talk, we're going to go over some of the things we're working on at the Samsung AI Center in event-based perception. This includes our work in efficient event-based classification, low bandwidth event-based classification, fast motion understanding, and our ongoing work in perception action systems. The first work we're going to present is our work on-device event filtering with binary neural networks for pedestrian detection using neuromorphic vision sensors. So this first work was motivated by the application of always-on applications. So always-on applications are things that are constantly running, and we may have some sparse stream of possibly detections or other outputs that are output over time, but these are things that are always running. We want them to be lower energy overall because we're going to be in some energy-constrained environments. The particular problem we were looking at was pedestrian detection. So these are always-on systems, again, energy constrained. If you're going to have them running on, for example, a wall with a battery, we need these things to be very low power overall. The current solutions to this, we're using convolutional neural networks. We're trying to classify things online, trying to see if something is there or not. But these require these intensive operations. So what we were looking for in this work was a low complexity architecture that can enable these always-on pedestrian detection applications in a simple manner. And one way to do this is using the efficiency of the DVS coupled with some on-chip detection algorithms. And that's our next step of our method. In our method, we first have this unfiltered event stream, which you see over here to the left, which is of a person, for example. One of the first things you'll notice or can see is there's a good amount of noise in this event stream up front. So we've coupled a few things to get our filtered event stream, which is our next step. And how we do this is we use our point process filter, which is basically a sequence of steps that denoises and aggregates information in the event stream. We're basically removing the noise, and then we are aggregating some of our edges here to be a constant thickness so that it's useful for classification. After we have that filtered event stream, we now run this through our binary neural network, which is combining the binary efficiency of the point process filter along with the binary neural network to get very efficient classification. And here we are basically taking this windowed input and doing a simple pedestrian detection task where we're trying to determine is there a human in the frame or not. And we do this all with simple instructions overall, which is great. Looking at what we did to actually train our network, here's our pedestrian detection dataset. You can see on the top various pedestrians walking around that we generated, and then a bunch of negative examples of different objects, boxes, sticks, and other visual stimuli in the field. We split our network to train this with 80% on our training dataset and 20% on our testing dataset. What we were able to show next was that our point process filter does a good job at reducing the noise and dimensionality of the data. Compared to just taking the raw event stream with the noise included, our point process filter increased the detection accuracy by 23% compared to the raw event stream. Additionally, we have done a study of basically accuracy versus network size. So we show going from floating point 32 to floating point 16 to integer 8 to a Boolean network. In our testing set, we only sacrifice about a 1% performance degradation from the full floating point 32-bit network. So we can enable these applications to run on small embedded processors that can be in these always-on situations. So we were able to determine that our point process filter was able to boost our classification score by 23% compared to the noise event stream. Our detection module has a low memory footprint overall, so this enables embedded applications for dynamic vision sensor classification in these low complexity environments such as home security, smart cities, and other areas where this might be important. Our next step was trying to actually see what it would be like to implement this architecture onto an accelerator, and what are some interesting optimizations we can do there, and how can we use this in a variety of environments. This next work was NearChip dynamic vision filtering for low bandwidth pedestrian detection. So the problem we looked at solving and what motivated sort of this work was then trying to use dynamic vision sensors in these IoT detection systems. So one of the big problems is that the DVS has this high bandwidth stream, and if we're looking to apply DVSs to low bandwidth networks such as LoRa, where you can get kilometers range, but you need a low bandwidth overall. So we looked at developing some on-chip compression algorithms for the event stream compression, and then couple this with edge compute classification using binary neural networks. Like we said before, binary neural networks are very nice for the efficiency that they have. So compared to integer inputs where you might have to use addition and subtractions, with a binary input and binary weights, we can use these simple AND and pop count instructions to perform our classification. So looking at our method, in a different lens now, we looked at the bandwidth over time of the various steps in our process. So we have our event stream again, where you can see now clearly the noise that you have in this event stream. Our next step was removing that noise. So we do this coincidence detection operation, which is a simple logical AND between two pixels. The next step after that is aggregation. So we want to have constant thickness edges so that we have the same movement of a person. Due to the motion here, if we have fast motion, we may want to correct more or less events depending upon what edge thickness we want to run through our binary neural network. So what you see here is that you may not get an edge every frame, so you get the sputtering of frames due to the fact that this may be integrating over time to have a better constant thickness edge. After that, we have our subsampling encoding operation, where we take our image and we subsample it, since the binary neural network does not need the full resolution. And then finally we code it using a Huffman code to further reduce our bandwidth here. What we studied next was the bandwidth reduction we received from these various modules, and then the accuracy or testing F1 score based on different combinations of them. We looked at first the coincidence detection, which gives us the spatial reduction and max pooling also, the aggregation in Huffman, which gives us the temporal reduction, and what we found is that our full architecture results in a 99.6 reduction in the bandwidth with respect to the raw stream, and then a 20% increase in the testing F1 score. These results showed us that our filtering module is able to reduce this bandwidth and increase our testing F1 score. This enables the application of dynamic vision sensors with some NearChip filter to be applied to low bandwidth IoT networks. What we're possibly looking at in the future of this is possibly looking at integrating this into an ASIC, improving the compressor in terms of reducing the bandwidth further, and how can we possibly incorporate multiple sensors to enhance the detection performance of our algorithms. Our next work looked at fast motion understanding with spatial temporal neural networks and dynamic vision sensors. We looked at the scenario of mobile robot systems that need to react quickly to rapid motion in dynamic environments. This could be forests, where we have a quadcopter moving around and it may need to avoid incoming debris very quickly. This could be a kitchen where we need to understand the people that are moving around us or make rapid action in order to avoid collision. This could be in roads where we're looking at various autonomous moving cars and we need to understand our environment very quickly to make life-saving decisions. So we looked at the problem of high-speed motion understanding. The current solution to this problem is mostly using active sensors such as LiDARs, radars, or IR depth cameras. One of the things that we looked at here was shooting a very fast moving dart around 30 meters per second at an active IR depth camera, and we find that we're unable to resolve the actual image here. So these things also have spatial constraints that we need to be very wary of when trying to choose systems to do these high-speed motion understanding tasks. What we were actually looking into is more passive sensors that would be able to survive on mobile robot systems for a longer time and allow us to get this high-speed perception information still. So we showed you down here to the right using a dynamic vision sensor, and you can see here the event video and some feature tracking of looking at the same dart being shot using the depth camera with a dynamic vision sensor, and you see we can get more perceptive information out of this. This led to our next problem of trying to look at biological motion understanding. So what sort of motion information do we look at and what is used there? So in animals, they look at these motion cues. So for example, when an object is increasing their visual field, they're receiving some looming response, and from this looming response, they're actually doing a quick planning and actually planning escape behavior based on this looming response. This motivated our idea of inspecting spatial temporal patterns of the event stream in order to create efficient avoidance maneuvers. This then is our method that we implemented this as. So our first step was acquiring the event-based camera output, which is our traditional XY polarity and time. We then encode this using a bank of exponential filters per polarity and per pixel. Basically what is happening here is we look over various motion lengths in some sense. With our small sort of filter here, looking at, for example, a 400 microsecond area, you're going to see the most recent motion. But if you look at something like a 0.2 second exponential filter, you're going to see a longer portion of the motion. So we looked at creating a sampling of these sort of motion lengths, and from here we use these in a convolutional neural network to extract spatial temporal features to then predict out our regress quantities, which were time to collision and impact location. And this end-to-end then can be used in a possible avoidance system based on seeing a small time to collision, you need to perform your avoidance maneuver, and then knowing the impact location, you can know where to move away from. To train our convolutional neural network, we record the devious events and object location while the object is approaching the sensor. To record the location, we locate the object with a motion capture marker, and our motion capture system will give us the location information for the moving object. We also record the set of events from the DVS. For a ball, we drop this towards the sensor, and for the dart, this is flying towards the sensor. Showing you an example now of what this data looks like. We're showing here an example of the toy dart, which has a speed range from 16 to 23 meters per second. Our initial range is around 0.6 meters to 1 meter. Our time range is around 26 milliseconds to 46 milliseconds. We also have a ball dataset, which has a speed from 1.2 to 4.8 milliseconds, an initial height of 0.4 meters to 1.2 meters, and a time range of 183 milliseconds to 352 milliseconds. All of this data is 240 by 240 unsigned 8-bit integer examples. One of the problems with our data collection process is the time consuming process to collect the limited samples. So we looked at creating a procedure to augment our data set so that we can increase the size to work on other real-world examples. To do this, we create an augmentation procedure. This procedure consists of applying a transformation to our event set. It's a translation and/or rotation where we basically create a new trajectory from this. And what we do to create this new trajectory is take each of the event sets at a given depth, apply the transformation, and then re-aggregate these into our exponential filter to then train our convolutional neural network. We now show an example of end-to-end, what our network looks like performing inference. So on the top left you see here a log polar grid, which is our output representation of our impact location. Our red point here shows you the example of the predicted region, and the green is the actual region that the object is going to impact. Our next plot shows you the exponential filter. The next two plots are an integrated example of the filtered probabilities for the radius and theta prediction in the log polar grid. The bottom left shows you the instantaneous probability estimates. And finally, we have the time to collision, which we see goes down overall. So we can integrate this information then into a real-time system to avoid or possibly try to move away from the incoming stimuli. Overall, our results from this showed us that we can develop an efficient architecture for motion understanding using event-based sensors. We have a data collection procedure which is useful for generating these networks and using end-to-end. And we also have a data augmentation procedure which can take real-world data and augment this to create more data for training spatial temporal models. We show that we can estimate impact location and time to collision for fast-moving objects. And then we are looking next to develop this integrated real-world system of showing this end-to-end. And this leads to our ongoing work of high-speed perception action systems with event-based cameras. Showing you our test bed for a second, we have our DVS, which is connected up to our computer, which runs our stack here, showing you an example of our driver here, which could be something like libUSB, which is gathering the packets from the DVS, parsing out these packets, some event-based algorithm then to actually determine when you need to move, sending out a serial command, which then goes to a motor controller, which controls a rail where your object or your DVS may be located, and you're trying to avoid this overall. And one of the big things we tried to do here was understand the full latencies of the system. And there are many of them that we need to characterize and figure out to optimize the entire setup. To do this first set of latency measurements, we need to know when the actual object is leaving or starting the motion. So we developed this start detector, which is an LED in a photocell, which can determine when our toy dart is leaving the barrel, and we can determine then when it hits the DVS or when it's going to approach the DVS by the glass in front of it with an accelerometer. So we can see when this spike occurs in the accelerometer movement to determine how long the motion was and what sort of parameters we need to optimize there. Looking into a little bit more detail here, so we had an observability delay, which was one of the first things we looked at, and this is basically the time between the Nerf gun that we're using triggered to the dart being minimally observable in the camera. And the dart is only around 12 millimeters, and we're shooting this around 5 meters away. And our initial DVS examples, this was around 100 milliseconds to actually get the dart to be observable in the field of view. We looked next also at the communication delay, so the time between a stimulus onset to this being received on the actual host. And we characterized this to be around 4 milliseconds. We also have a serial latency of around a millisecond till it's actually starts to move the motors. And then we have an action latency of around 33 milliseconds to move the distance of the dart to avoid it and not collide with it. To fix the observability delay, the first thing we did was we tried to use some optics to help us. Reduce our field of view, but increase the size of the things in our field of view so that we can use these to determine quickly when we should move away. And showing you an example now of what this actually did for us. So what you're going to see here in the blue is the photocell. So you'll see a quick spike, which is basically the dart is leaving the photocell. And then the next important thing is this purple, which is basically the time at which we're going to trigger our motion. And then the green is the start of the accelerometer, basically collision. And what we want is we want to have at least 33 milliseconds between our purple and green signal. So originally we had 21 milliseconds, but by adding these optics in, we're able to do this and gain 106 milliseconds between our motor trigger and the accelerometer actually being triggered from the collision. So now showing you this in real time. Now I'm going to show an example of applying our system end to end. What you'll see is that we have our fast approaching dart, you'll see here in this location to the left, and our target is avoiding this, doing a real-time dodging task, applying our end-to-end procedure for event-based perception for this obstacle avoidance task. And we can see we're able to successfully avoid the dart in all cases. Our next video is going to show you a slow-mo of the fast-moving dart approaching the target. We are able to successfully avoid this pretty early on in the motion and perform this sense plan act in a very fast and tight manner. So this is useful for developing these tight perception action systems which can avoid fast incoming stimuli. So overall, we were able to explore these perception action systems and the system latencies present. We found that optics can improve the visibility of the objects and be useful in our setting. We found that our action latencies remain a large component of the end-to-end system latency, so trying to use this in the real world. We still need to be able to move fast if we can get very fast perception. Our next steps are possibly to improve our terminal state estimation, investigate other applications where this rapid sort of state estimation may be important, evaluate more predictive methods in terms of what we could use this event-based perception to help us with action for, and then also some unsupervised methods possibly for this perception. This showed you an example of some of the work we've been doing at Samsung. If you have any questions about the work we had in this presentation, feel free to email us at the email provided below. Additionally, our team at the Samsung AI Center New York is hiring for research engineers and research scientists. Feel free to check out our job postings online. Thank you.